Good morning everyone, my name is Francesca Palermo and I'm a PhD candidate at Queen Mary University of London in the Advanced Robotics Lab. I will present here today my work on automatic fracture characterization and localization using both proximity and tactile sensing, and I hope you will enjoy it. One of the most important tasks in extreme environment is the detection of mechanical fracture on objects, such as containers, which are used for keeping chemical and radioactive waste. The problem is that these fractures need to be detected at early stage to avoid bigger failure later on. The majority of existing techniques rely on visual method or eddy current. The problem with vision is that it can fail when the luminosity is limited and are not capable of acquiring mechanical feature of the explored object. Eddy current methods rely on a banded sensor, which needs to be included in the structure when building it. Both of them are affected by the gamma radiation in nuclear environment. On the other hand, tactile and proximity provide important material properties such as shape and textures. A sensor with a fiber optic mechanism has been chosen since the fiber optic sensing mechanism is not affected by the gamma radiation which are found in nuclear environment. In addition, this sensor does not have any onboard electronics which would be quickly destroyed by the radiation in a nuclear environment. And here the video briefly shows an example of movement on the explored surface, but I will later explain the methods and how the sensor works. The sensor implemented in this study is a fiber optic-based finger-shaped sensor developed at the Advanced Robotics Lab at Queen Mary University of London by Jelizaveta Konstantinova. It is constructed with a rigid base and a rigid tip 3D printed with fiberglass, and in the middle there is a semi-flexible element 3D printed in nylon. Each signal is made up of a pair of fiber optics. One is used to emit the light, while the other receives the reflection of the emitted light. It consists of 3 pairs of fiber optic to detect the deformation of the sensor on the left and the right side and the normal force. An additional pair of fiber optics is used to calculate the proximity of the explored object. In this work, we propose a machine learning-based technique to classify fracture and bumps based on the deformation and proximity signals. If a fracture is detected, its width is classified. The sensor is attached to a Geomagic Touch, which is a robot especially used in haptic and medical related research, since it provides haptic feedback to the user. The sensor will then slide across 3D printed surfaces and will acquire deformation and proximity data that will later be classified. In the paper submitted to ICRA, only offline classification was provided, but we have uploaded the methods to implement also real-time classification. So I will present here the final version of the proposed method, which is awaiting final review for a journal paper. The sensor slides across the surface to explore, and in case of the offline classification saves the data in CSV files, which will be later analyzed. Tactile proximity signals from 12 repeated continuous sliding movements are recorded, and this continuous recording is reiterated 5 times to avoid the training and testing on the same session. The tactile sensor is moved across the 3D printed sample object, which are shown in this slide. They consist of no crack, crack, bump, and wavy pattern for the crack recognition, and for the width classification, we have been printed it's in 5 different sizes. Here you can see an example of the pattern of the acquired signals. The right deformation was pretty noisy, but this has been solved at the moment by changing the cables and performing new calibration. The normal force signal data is not that sensitive because since the sensor is sliding from left to right and backwards across the surface, there is not enough normal forcing applying on the sensor. For the feature extraction step, 2 features are computed, the mean absolute value and the root mean square. These features are time-based ones, so they are really fast to compute, which is good for the real-time setup, but they are pretty sensitive to noise, so outliers need to be removed before the analysis. Classification is implemented with the random forest classifier with 100 trees. The random forest has been already evaluated for remote sensing, and it can successfully handle high data dimensionality since it is both fast and insensitive to overfitting. In addition, we also use KNN with 5 neighbors and quadratic discriminant analysis for comparison reasons. Following main machine learning work, the data is split 70% for training and 30% for testing. The image on the right shows the distribution of the data based on 4 classes, so no crack, bump, and wavy pattern, and example of the classification map of one of the learning trees of the random forest. To remember, here the last version of the setup is being described. For the classification, first row, mean absolute value, and root mean square data are classified using only the proximity data or the force data, so D1, D2, and D3. Then the row, mean absolute value, and root mean square with all the data, so proximity, D1, D2, and D3. And in addition, the random forest allows calculating the importance of the different signals used for the classification. From this analysis, it is shown that D3 signals is the less important for the classifier's analysis. So the classifier is also trained and tested on proximity data P together with D1 and D2 force data without using the D3. As you can see from the results of the offline analysis, the classification accuracy achieves over 90% when training and testing with the mean absolute value or root mean square feature with a force plus proximity, or also with the left and right displacement plus the proximity. So, as the random forest signal analysis suggested, it is not necessary to analyze the whole set of displacement, but we only need the left and the right one. In this case, the random forest is the best classifier among the 3 classifiers. I will briefly show also the random forest results. From the confusion matrix, it is possible to see that the most difficult class to classify was the bump, since it is mostly mislabeled with a wavy pattern, which is understandable since they are physically similar. Regarding the real-time results, 3 continuous sliding movements were performed on each crack type. All the combination of proximity, displacement, and features were performed, which ended up in a total of 432 classified movements. In this case, the KNN achieves the best results. It is necessary to know that the KNN works well for these data that were classified since they are well divided. In addition, these results may be due to the limited number of sliding movements performed for each combination, so additional analysis will be performed to investigate the results. All the previously described research is applicable in a supervised and controlled environment, but when we move ourselves in a real environment situation, exploring the whole surface with only a tactile approach will be time-consuming and may produce many errors. For this purpose, I am working at the moment on developing a multimodal approach fusing both vision and force proximity data. It implements a faster RCNN neural network for object detection, so the main idea is to recognize and localize the cracks in the environment, and once the faster RCNN model calculates the bounding box location for the cracks, they will be sent to the manipulator, which will move the sensor to explore the identified surfaces, and we confirm if there is a crack or it's just a false positive. Preliminary results show promising results, but the model still needs to be improved. In conclusion, this work demonstrates how tactile and proximity sensing can be implemented for fracture recognition. Future research will consist in testing the model in a realistic extreme environment. In addition, a teleoperation system will be developed to provide haptic feedback to the user and a visual reconstruction of the explored surface in Unity. So thank you everyone for your attention. If you have additional questions, please contact me on the provided email, and enjoy the rest of the conference.